Hello and welcome to today's episode of Deconstructing CDK patterns. Today we will be discussing the event-bridge-etl pattern, which is made up of the following AWS components: AWS S3, Fargate, EventBridge, Lambda, and DynamoDB. The event-bridge-etl is designed to take a CSV file that has been uploaded to S3, extract the contents, transform it into JSON, and insert the data into DynamoDB. You would call this a standard ETL process. Something that I particularly love about this implementation is that it's a fully event-driven architecture. This decouples all the components from each other, with the process flow being controlled by event-bridge rules. In real terms, if you ran this process for a 5-record CSV file and didn't like how 2 out of 5 of the records were transformed, all you would need to do is write a new transformer lambda for the records, create a new event bridge rule, and rerun the original events. All of the components used are on the far right of the serverless spectrum. This makes this massively scalable, cheap to run, and fast. Finally, observability is a strength since all the components are emitting multiple events. These events can all be seen in the logs for the observer lambda, which tells you exactly what happened at every stage of the process. There are a couple of things that you should consider before using this pattern in production though. The first one is checks and balances. You should be checking if the contents that are in DynamoDB at the end of the process are the same as the contents that was in the CSV file uploaded to S3 at the start. This wouldn't actually be a significant effort as we already have the observer lambda with all events, so all you would need to do is marry the extraction events, the ID of the record, with the insertion events into DynamoDB. The next thing that is not included is error flows. I didn't include error flows to try and teach you the core concepts without overwhelming you with extra steps and flows, but this would just be another event sent onto EventBridge with a rule directing them to an error hospital or a retry flow. Before we go any further, if you want to get the code, as always, you can use our cdkp command line tool. So for the TypeScript implementation from a command line or terminal, just run npx cdkp init the-eventbridge-etl. For the Python CDK implementation, it's the same command, except for adding on --lang equals Python on the end. Finally, if you don't want to clone the code, but you do want to browse through it or read where this pattern came from, you can go to github.com/cdkpatterns/serverless. I'm going to break down the pattern piece by piece, but before we do that, let's just take a 30-second sweep across the whole pattern and make sure that everybody understands where we're going. So on the left hand side, you will see the user uploads a CSV file onto Amazon S3. This triggers a creation event to be sent onto an SQS queue, which is consumed by an extract lambda. This extract lambda kicks off a Fargate ECS task, which downloads the file from S3, sends each row as a separate event onto EventBridge, which are then sent via a rule to the transform lambda in the top right, which converts that CSV format into a JSON format, sends another event back onto EventBridge, where a rule sends the event into the load lambda in the bottom right, which puts it into DynamoDB. After that record has been inserted into Dynamo, a final load event is sent onto EventBridge. All of those events are consumed by the observer lambda at the top, which writes every event to CloudWatch. Now to start breaking down that full flow, and the first step is that we have our data upload to S3. This is the testdata.csv file that is included with the pattern by default. You can see that it is address information. The file itself contains 5 rows with columns that are ID, house num, street, town, and zip. If you've never seen a CSV file before, you can see at the bottom that each row is just separated by a new line, with each column separated by a comma. After we upload our file to S3, an object creation event is sent to our SQS queue. We then have a throttle lambda subscribing to that queue. If you look at the JSON in the middle of the screen, that is a stripped back version of the message that is sent. Two things to note at this point are that the file contents are not part of the message and the Lambda does not download the file. Now, before we move on to the next step, I wanted to tell you why the Lambda is throttled. Every single Lambda in this whole pattern is throttled down to 2 concurrent executions by default. I did this because this is a massively scalable pattern. Every row in the CSV gets processed separately and at multiple stages. If you are sharing your AWS account with anyone else and uploaded a large file, say 100,000 records, you could consume all Lambda capacity on that account and stop others from working. So if you want higher concurrency, I will show you how to configure it in the demo later on. The next step in the process uses a Fargate ECS task, so I thought it'd be a good idea to just take a couple of seconds and talk about what that is and how it fits into the serverless spectrum. So if you haven't heard about Fargate before, this is Amazon's serverless container offering, and if you're not sure what I mean by that, let's just jump to the next slide which talks through the serverless spectrum. This image is actually a couple of years old, so you'll notice that some of the newer services are missing, but it still makes a very valid argument. The question of whether a service or component is serverless is not answered with a simple yes or no. You can base it on the level of burden of maintenance on your organization. So if you think about it like this, you have the on-premises solutions on the left. Now, they not only require you to keep the version of the service up to date, but you also need to maintain the building, the cleaners, everything around that just to keep that service up and running. Now, you might also be thinking, because I said that if you use Lambda on the right, it can be seen as the holy grail of serverless, but I would argue that you can still have a non-serverless Lambda implementation. If you, with Lambda, build your own custom runtime, and then you combine that with the Lambda-lith pattern that you can learn more about in the Lambda Trilogy video, and then inside that Lambda-lith pattern, you install a web framework. Are you really building a serverless implementation? I would say no. You're now maintaining a custom runtime as well as all the dependencies for that framework inside the Lambda itself. So you've pushed yourself left on the compute spectrum. The same can be argued with Fargate as it lives just above Lambda on that spectrum. Out of the box, Fargate is just a container that is slightly bigger than the container offered by Lambda. Lambda restricts you to just pick, I want this language and I want this amount of memory, whilst Fargate lets you pick the actual container that is running. So depending on what you put in that container, as far as I'm concerned, dictates how serverless your Fargate solution actually is. To follow up then my opinion with the official Amazon definition of ECS on Fargate, AWS Fargate is a technology that you can use with Amazon ECS to run containers without having to manage servers or clusters of EC2 instances. With Fargate, you no longer have to provision, configure, or scale clusters of virtual machines to run containers. This removes the need to choose server types, decide when to scale your clusters, or optimize cluster packing. When you run your tasks and services with the Fargate launch type, you package your application in containers, specify the CPU and memory requirements, define networking and IAM policies, and launch the application. Each Fargate task has its own isolation boundary and does not share the underlying kernel, CPU resources, memory resources, or elastic network interface with any other task. To summarize then, Fargate is a container that you pick the CPU and memory requirements, you define the permissions through IAM, and then you decide what it's allowed to network with. It's as simple as that. As of April 2020, this table contains the list of valid CPU and memory values that you can pick when standing up a Fargate instance. You can see that the smallest CPU value is called 256, and that relates to a quarter of a virtual CPU with memory from 0.5 GB up to 2 GB. The largest Fargate instance that you can configure is called 4096 in terms of CPU, which gives you 4 virtual CPUs, and it can have anywhere between 8 GB and 30 GB of RAM. Jumping back then to our EventBridge-etl pattern, Let's just recap on where we are in the flow. Our extract Lambda has just received a message from SQS containing our file name and our bucket name. It now is going to kick off a Fargate ECS task. This task is just a simple Python script that uses the AWS SDK to download our file from S3. It knows where the file is because our extract Lambda passes in file name and bucket name as environment variables. Given, you can see in the bottom right that I used the smallest container settings, and this is a simple Python script. Let's just discuss why the Lambda didn't download the file itself. For this tiny 5 record file, Lambda absolutely could have done the work off Fargate here, but in real life, you're going to be working with files in the terabyte or the petabyte size range, which will need the flexibility of Fargate. There are Lambda workarounds, but honestly, Fargate will be cheaper and more flexible for large workloads at the end of the day. Now that we have our file downloaded into our Fargate container, it's time to extract each row and send it as a separate event on EventBridge. You can see on the right side of the screen that EventBridge events follow a standard envelope. The envelope contains detail type, event bus name, source, time, and detail. First up, detail type you can think of as what kind of message is this, and this is mostly used for writing rules later. Event bus name allows you to specify which bus you want this message to be sent to. So for the sake of simplicity, this pattern uses the default, but you probably want to define a custom one for this. Source you can think of as the name of your application or bounded context. Time is the time of the message, and then detail is the payload itself. And you can see because the payload is a JSON object, that allows us to write more intricate rules later. We now have 5 separate events on EventBridge on our default bus that are represented by the yellow boxes at the top of the screen. You can see that I've just shown the actual payload itself to save screen real estate, but the rest of the envelope would be there. These events are all sent to a transform Lambda through an EventBridge rule. Now it's important to note that it is 5 Lambda invocations and not one invocation containing all 5 events. That transform Lambda takes each event in turn and transforms the header string and the data string into a combined JSON object in the payload of another EventBridge event. That transformed event is then sent through another rule to the load Lambda that inserts the data into DynamoDB. Finally, a load event is then sent back onto EventBridge, just containing the record that was just inserted into DynamoDB, which gets consumed by our observer Lambda at the top. Now that we have seen the full flow, let's do a quick code walkthrough and demo of the CDK implementation using Cloud9. Jumping into Cloud9 then, the first thing we need to do to get access to the codebase is to run the cdkp command that we saw at the start of the video, which is npx cdkp init the-eventbridge-etl. What this does is goes off and does a shallow clone of just this pattern from cdkpatterns.com, runs a build, installs the dependencies. While that's going on, just to show you that every pattern on cdkpatterns.com includes the outputted CloudFormation template for this entire pattern. So you can always, even if you don't know CDK, but you want to know how this would be represented in CloudFormation template YAML, you can always come in here and grab the template. The template for this particular pattern is 1143 lines long, we'll call that, so you can compare that to what it looks like in a CDK stack in a minute. Now that that has finished, we can jump into the folder. Every pattern also includes a comprehensive suite of unit tests, and the reason why these tests exist is because we need to make sure that the CloudFormation that you just saw matches what our expectations were at the start whenever we went into this. And as you can see, we ran 18 tests and all 18 passed. It takes quite a long time to deploy this pattern, so I'm just going to go ahead and kick it off. Now, I was slightly disappointed in the syntax highlighting for this particular pattern in Cloud9. So in order to make it a slightly better viewer experience, I'm just going to jump over to VS Code, but this is the exact same code base there is no difference here. So if you jump inside lib/the-eventbridge-etl stack.ts, this is where the vast majority of our logic lives for our CDK setup. You can see at the top that we're actually using quite a lot of different parts of AWS to make this happen, and I think that's pretty cool. Now, at the top, I mentioned whenever walking through the theory that I would show you how to change the amount that your Lambda has been throttled. This is a constant defined at the start of the file, and it's set to 2. If you want to raise the concurrency of every single Lambda in this stack, you can just up this value here. Otherwise, in the Lambda definitions later on, feel free to override it. The next thing we have is our DynamoDB table, and you can see that it's not set up in a complicated manner. It just has a partition key, and that partition key is called ID. There's nothing strange or wonderful going on with that. This is our S3 bucket. Now, I should point out at this point that if you are going to use this pattern in any kind of real context outside of learning, you should be encrypting this bucket and making sure that it has the right access policies so that you do not lose any data. This is just an S3 bucket created bare bones. Now we have our SQS queue, and remember that whenever the object is uploaded to S3, that triggers an S3 object creation event to be sent to SQS. So this is that SQS queue. In order to connect the bucket with SQS, all we had to do was bucket.addEventNotification, S3 event type object created, and then say it's an SQS destination, and we want it to go to our queue. This IAM policy statement is used in multiple places throughout the rest of this file, and it's simply to say that whatever this is attached to is allowed to put events onto our event bus. This is the section relating to our Fargate instance, and you can see that there's quite a lot of different components that you need to stitch together in order to stand up a Fargate ECS container, but I'll just briefly walk you through it. So in the definition, I mentioned that Fargate allows you freedom of network, IAM permissions, container type, and then memory size and CPU number. So in order to do the networking piece, you need to set up a VPC. And these 3 lines between line 68 and 70, that is the minimum amount that you should really need to write to set up a VPC. You can write a lot more sophisticated and complicated setup, but again, remember, this is just a learning pattern. Lines 72 to 75, that's just log retention. So all we're saying is whenever the logs come out of this container, we want them to have a prefix of the event-bridge-etl, and we only want them to stay for 1 week. 77 to 79 is referring to our ECS cluster, and that is because each Fargate task has to live inside a cluster, and a cluster has to live inside a VPC. So you can see that we just give it the VPC that we defined a couple of lines above, and that's how we do our task definition linking through to the networking piece. Finally, on lines 81 to 84, you can see that we have our actual Fargate task definition, and all I'm setting is the smallest CPU type and 0.5 GB of RAM. Next, we need to give our Fargate container permission to put events on EventBridge. So that uses the policy that we defined slightly earlier. And then we need to give it permission to actually read the contents of our S3 bucket. Finally, we need to actually tell Fargate where our container is. Where's the Docker image? So this is a task definition .add container. The image is found in the container/S3 data extraction task folder. We want to give it the logging policy we defined just a couple of lines above. And then these are the environment variables I mentioned that are used to tell it where the bucket is and where the object is. So just to show you, if I go to container/S3 data extraction task, you can see that there's 4 files in that folder. But really the one you should be most interested in is main.py. And this, as I mentioned earlier, is where the standard Python logic lives for pulling down the file, extracting all of the rows, and uploading them each as an event on EventBridge. So these are the 2 lines where we pull out the environment variables that I just showed you. If they don't exist, if whatever reason, throw an error. Where we're going to pull this content down to is a local file called temp/data.tsv. And then we just use boto3 to say s3 resource.object. In this bucket, this is the object name. Download that file to our local file. So that now is all the logic that we needed to go out and pull down that file that we uploaded into the S3 bucket into our Fargate container. The rest of this logic uses a CSV file to extract each of the rows. So the first row is always the headers. So it just pulls off the header row and then loops over all of the rest of the rows and sets up our EventBridge envelope based on the data that was contained within. And you can see that the event object here is what's contained in the EventBridge payload from down here. And headers and data are just a string separated by commas. And then to send this event to EventBridge, all we need to do is do eventbridge.putEvents, and that's everything. This script exits also after it's finished, so this is not a long running task. This is a one and done. Now, the next phase of this architecture involves our lambdas. If you remember, we have 4 different types of lambda in this architecture. We have extract, which takes the data from the SQS and kicks off our ECS task. We have transform, which takes in the 2 strings you just saw coming from Fargate onto EventBridge and transforms them into a JSON object. We have the load lambda, which inserts the records into DynamoDB. And then finally, we have an observe lambda that just watches everything and logs what it sees centrally. The extract lambda is actually the most complicated one of the bunch, and that is because it needs permissions to read from SQS, and it also needs permissions to kick off our ECS Fargate task. Plus, as a bonus, it also sends events to EventBridge. It's not represented on the diagram, but every single component in this architecture sends an event to EventBridge that is consumed by the observer lambda. So that's why this extract lambda takes its code from lambdas/extract. So lambdas/extract. The logic lives inside S3 SQS event consumer, and it's a handler method inside there, which I'll jump into in a minute. Our reserved concurrent executions is set to the constant at the top of the file. And then in order for it to be able to kick off a Fargate ECS task, we need to give it some information. We need to tell it our cluster name that we defined earlier, our task definition ARN, our subnets inside our VPC, and then finally our container name. That's all it needs to be able to kick off this task. But in order to give it permissions to do all of this, we need to take our SQS queue and grant consume messages to this extract lambda. We need to add an event source to the lambda of SQS, and then we need to give it permissions to put events on EventBridge. Then, in terms of actually kicking off a Fargate ECS task, it needs these 2 policy statements. One allows ECS run task, and for certain tasks on AWS, you need this IAM-pass rule, so it needs both of them, and it's just done through extract lambda.add-to-role policy. And to jump inside that lambda itself then, you can see that at the start of this lambda, all we're doing is checking that those 4 variables we need to start our Fargate task are present. If not, we throw an error. Then further on down, we create this params object, which is used in the actual SDK call to ECS. So we just say cluster is the cluster name passed in. We want it to be Fargate. Our task definition is the ARN that was passed in. We only want one. We want to use the latest platform version and then use the subnets that were passed in. Then what we need to do, because the message that came in from SQS is actually an array, we need to just loop over a couple of levels deep because it's an array in an array. And from there, we can extract the object key bucket name and bucket ARN from that event. And if they are not undefined, what we can do is this section here. What you're able to do is override parameters on the task definition. And that is why I mentioned that I pass the bucket name and object key through environment variables. Well, this is how you do it. You just say params.overrides, container overrides, environment, which is an array, and then give it the names and values. And then make sure you specify the container name in that object. This is then used, as you can see, in our ecs.runTask params, and then the response is logged out, as well as we then go to EventBridge, where this is our EventBridge envelope, detail type.ecs started. You'll notice there's no rules anywhere for detail type.ecs started. Our source is still cdk patterns.the-eventbridge-etl, and then the data inside the body is the ECS response that came back from that run task command. So we're just able to do eventbridge.putEvents and then throw any errors that come out of that. Now we have our transform lambda. This is a lot more straightforward. This lambda just takes in that object that was just sent from the Fargate task and transforms it from strings into JSON objects. So the code for this lives in lambdas/transform. Just minimize that. Transform. And all this does, it's quite simple really. So the object comes in and it has a headers property in the detail of the event, event.detail.headers, event.detail.data. And these are both strings that are separated by comma. So I just split the two objects on comma and then just smooshed them together would be the technical term. So if the data at array index 0 is called the header at index 0, so that just puts it into an object. Then again, this will become quite familiar, this params object. You can see we build up our EventBridge envelope of detail type transform, source, cdk patterns.the-eventbridge-etl, but this time the detail is actually our transformed object. And then this logic's just boilerplate for put events. This section here from 167 to 177, this is our rule on EventBridge. So this is how it knows which records, or which events I should say, to forward to this lambda. So it's looking for events of type S3 record extraction with a status of extracted and a source of cdk patterns.the-eventbridge-etl. Now, if we go back to our main.py, you can see that the detail type of the events that were put on the EventBridge were S3 record extraction, the source was cdk patterns.the-eventbridge-etl, and the status in the actual payload was extracted. So that's how those two things link. This event gets routed through to the transform lambda through this rule. And in order to hook those two things together, it's just a case of saying transform rule dot add target lambda function transform lambda. Next phase of this process is our load lambda, which takes another event from EventBridge, takes the object off it and inserts the information into Dynamo. So it just exists in the lambdas/load folder. And it needs to take in, as part of its environment variables, the name of the DynamoDB table. And we also need to give it permission to actually write records to this table on top of the EventBridge permissions. So if I just jump into there, what we have here, we have to use DynamoDB to say we want to insert an item into our table that we passed in, and it will have ID, house number, street address, town, and zip. We await DynamoDB.putItem, and then based on the result, what we do is create another data loaded event that we send to EventBridge, where inside the payload we have status success, and then the object that we inserted into DynamoDB. And again, just EventBridge.putEvents. So you can see it's pretty cool that none of these lambdas know where the information is going after they finish. They just fire off an event and hope that something is going to catch it later. Now, finally, we have our observe Lambda. This is a Lambda. It doesn't actually have very much logic in it. So it lives in observe/observe.ts. All this does is literally log whatever gets sent to it. This is not a complicated Lambda. And it doesn't need any permissions because it doesn't actually do anything. It doesn't send events to the event bridge, doesn't read from Dynamo. So this is a really simple Lambda. The only thing that we needed to configure for it was this observe rule. And all this rule says is anything that has a source of cdk patterns.the-eventbridge-etl routed to this Lambda and then hooked together through this. So that's the code. Let's see if that has deployed, and then we could do a demo. Yep, this has deployed. So let us just jump into S3. We've got our new bucket. We want to upload a file. Now the file that we're going to upload lives in the data to upload folder, and it's called test_data.csv. So we're just going to upload this. And that is done. So that is everything kicked off. We can now go to CloudWatch, start refreshing log groups, and you can see that we have our Fargate task definition, we have our extract Lambda, we have our observe Lambda, and we have bucket notifications handler. If I refresh this again, we should eventually end up with load Lambda. But to start off in the extract Lambda handler, jump into the latest. You can see that this is saying that we have set up our field entry count. So we have kicked off our Fargate ECS task. And there we go. Here's our load Lambda handler finally ran. So load, where these are our events that come in from EventBridge, and then they have been inserted into DynamoDB. And if we go to our observe Lambda, go to here, we can see that we have a lot of events, and these are the different types of events. So this one is an extracted event. There's a transform event. And then there's a data loaded event. All in the one place, all together. And these are all pretty much in order, but because this is asynchronous and because we have a bunch of lambdas in play, you could notice that these appear in a different order. But this is now finished, so I can jump over to DynamoDB and look at my table. And there we go. There's the data that was in my CSV file is now in DynamoDB. So all I had to do was upload a CSV file into S3. That kicked off all of that process, which sent all the events to our observer Lambda, and then eventually the data ended up in DynamoDB. Final step that you should do is, after you've learned this, instead of leaving things running in your account, you can just run npm run cdk destroy. This will ask you, do you want to delete everything? And you can just say yes. You will have to go in and manually delete a couple of things. The first one is the S3 bucket. The second one is the DynamoDB. But it's always a good idea after learning how to do certain things to just tidy up your accounts. Okay, that's everything for this episode. So click subscribe if you liked what you saw. Come follow me on Twitter at cdkpatterns. Hopefully I will see you again. Thanks everyone.